We like similar matrices because similar matrices have a lot of the same properties. So if A and B are two similar matrices, if they are both two square matrices and they're similar to each other, then the determinant of A and B are the same. The rank of A and B are the same. The traces of the two matrices are the same. And they have the same characteristic equations and the same eigenvalues. Okay. Notice, by the way, generally, they will not have the same eigenvectors. A and B do not generally have the same eigenvectors. Okay, so we're going to prove each one of these. For most of them, they're pretty straightforward. So let's use our assumption. We're assuming that A and B are similar. So let A and B be two n by n matrices such that A is similar to B. Then there exists a matrix P. Let's specify the size. An n by n matrix P such that B is equal to P inverse A P. All right, so I'm just using the definition of similar matrices. That's all I'm doing so far. If A is similar to B, then B is equal to P inverse AP. Okay? And that's all we need to prove each of these results. So let's start with A. We want to show that the determinants are equal. Well, this is real straightforward because we know we can split the determinant up over products. Okay? Observe the determinant of B is equal to the determinant of P inverse AP. And because we could split the determinant up over products, that's the determinant of P inverse times the determinant of A times the determinant of P. And we know that the determinant of an inverse matrix is 1 over the determinant of the original matrix. These are properties of determinants we've already looked at, we've already proven. 1 over determinant of P times determinant of P, they will cancel, leaving us just determinant of A. So determinant of A is equal to determinant of B. All right? So A is done. B might be the trickiest one to understand. We want to show that the rank of A and the rank of B are equal. All right? So we're going to use elementary matrices here. Since P is an invertible matrix, P equals E1, E2, all the way to EK for some elementary matrices. E1, E2 to EK. So this is a property we've already shown. We proved this when we started looking at elementary matrices. If we have an invertible matrix, every invertible matrix can be expressed as a product of elementary matrices. Okay, so we're using that here. then P inverse AP is equal to, so we want P inverse, which is going to be the inverse of this. So that's going to be EK inverse E2 inverse, E1 inverse times A times P, which is E1, E2, all the way to EK. Okay? So the key here is realizing, so this is P inverse rather. This is P. The key is realizing we're just applying a bunch of elementary matrices. When we apply elementary matrices on the left of a matrix, that is equivalent to performing row operations. We know that performing row operations does not change the rank of a matrix, right? We will still have, the rank is defined as equivalently the number of non-zero rows of the matrix, but also the dimension of the row space or the dimension of the column space of the matrix. If we're applying elementary matrices, it does not change those things. If we multiply elementary matrices on the right, that's equivalent to performing elementary column operations, which we don't really do in this class, but the rank is still preserved for elementary column operations. This is equivalent to, let me rephrase that actually. That is multiplying matrix A by P inverse and P is equivalent to performing elementary row and column operations on A. Which do not change the rank of matrix A. Thus, the rank of A is equal to the rank of P inverse AP, because these are just the equivalent of performing elementary row and column operations on matrix A, doesn't change the rank. But P inverse AP is just matrix B. Okay, so the rank of A and the rank of B are equal. All right. For part C is real easy if we take into account what we've already proven about traces and products. Observe that the trace of B is equal to the trace of P inverse AP. Just substituting here, B is equal to P inverse AP, right? That was our original assumption here, since A and P are similar matrices. Okay, but we know that when we have a product inside a trace, the order doesn't matter. So specifically, if I kind of imagine grouping trace of P inverse AP, just grouping them a little bit differently, because trace of AB equals trace of BA. We saw that previously, right? I could think of this as the A in this statement, and this as the B in this statement, and then flip them around. Okay? So I'm going to get trace of, I'll put the AP first, and then the P inverse after. But that's just trace of A times P inverse. And P times P inverse is just the identity matrix, so I just get trace of matrix A. Okay? All right. Now, let's do part D and E. We're going to kind of do them the same time, because if two matrices have the same characteristic equations, then the solution to those equations must be the same also. If you have the same equation, you have the same solutions. And the solutions are the eigenvalues, right? Okay. Let me just write observe. Observe. So I'm going to start with the characteristic equation for matrix B. So remember, the characteristic equation is the determinant of the matrix minus lambda times I. The zeros of the characteristic equation are the eigenvalues, right? So I want to show that this is equal to the determinant of A minus lambda times I, and then the characteristic equations will be equal, and therefore the zeros of those characteristic equations, the eigenvalues, will also be equal. Okay, so to do this, I'm going to use the fact that B is similar to A and replace B with P inverse AP. And then I'm going to do something kind of clever here. I'm going to say, well, wait a second. Lambda I is similar to itself. That is, because matrix I is, it commutes with everything, I could do P inverse times lambda I times P. Okay? I could absolutely do that. Maybe just show you one way to argue that. Matrix I is just P inverse times P. Lambda is just a scalar, so I could move that in. Actually, before I do that, I can just stick matrix I in there because it's just the identity matrix. I times P is P, right? And then lambda is just a scalar. So I can move it wherever I want in this product. Okay, so that's one way to think about how I get from here to here. Right? Now what I'm going to do is I'm going to factor the common P inverse. I'm going to factor the common P. Be careful that you factor on the correct side. Remember, matrix multiplication isn't commutative, so I can't pull the P out on the left side because it's multiplying these two products on the right side. So I'm going to pull P inverse on the left side because it is on the left side. And I'm going to pull P out. I'm going to factor P out on the right side. All right. Now this is inside a determinant, and we already seen that with the determinant of products, I could take the determinant of each factor in the product separately. We've already seen determinant of P inverse and determinant of P cancel because the determinant of P inverse is 1 over the determinant of P. Since A and B have the same characteristic equation, which is what we just showed here, A and B have the same characteristic equation. They have the same eigenvalues. A and B have the same eigenvalues. The eigenvalues are just the zeros of the characteristic equation. If you have the same equation, you have the same solution to that equation. All right, and that's what we showed here. The characteristic equation of B is equal to the characteristic equation of A. So we've shown that their characteristic equations are the same and they have the same eigenvalues. So that's parts D and E right here. And again, I just want to emphasize, even though they have the same eigenvalues, they generally do not have the same eigenvectors.